Today's webinar topic is Optimizing Injection Strategy for Enhanced Oil Recovery. And with that, I will turn it over to our speaker, Senior Account Manager, Jelayne Fortin.
So today I'm going to be talking to you about enhanced oil recovery. So before I get into the details of what we do here at Interface, I'll just give a quick overview of why we care about enhanced oil recovery. So one of the most significant challenges that oil companies face during oil production is the low recovery of mature oil fields. A mature oil field is one where production has reached its peak and has actually started to decline. So the average recovery that we see from mature oil fields around the world is somewhere between 15 and 40%. And because of this, operators have attempted several different methods of enhanced oil recovery that offer options for improving recovery and accelerating oil production. So enhanced oil recovery can typically be divided into three main categories of chemical, thermal, and gas injection methods. In this webinar, we will explore each of these and provide you with examples of how our technology contributes to operators in this space. So Interface uses microfluidic technology that can help operators by screening different polymers, surfactants, CO2 foams, and other fluids that can assist in enhanced oil recovery. For gas injection, measurement of minimum miscibility pressure, or MMP, of various injected gas compositions and oils is a popular service that we offer. We also help quantify the performance of foaming agents, as well as looking at polymers, surfactants, nanofluids, amongst others. SEG-D is a form of thermal EOR that we also help screen for through the various additives that help supplement the steam stream. All of our measurements are repeatable, and our chips accurately mimic the pore throat size distribution, permeability, porosity, and wettability of the reservoir. And we run all of our tests at reservoir conditions using reservoir fluids. The best part of our technology, though, is that our high-resolution optical access enables visual quantification of performance in real time. So the first thing I'll touch on is polymer EOR, which is one of the main aspects of enhanced oil recovery that we look at here at Interface Fluidics. So I'm just going to explore here on this first slide how we use microfluidics to help us improve the enhanced oil recovery space. So polymer flooding is a popular method that can help increase recovery factors up to about 20%. Adding polymer decreases the fresh water consumption, it lowers greenhouse gas emissions, and it's also a bit more affordable compared to some other enhanced oil recovery techniques. The use of polymer helps reduce water cuts, as well as the amount of pumping energy required in the field. It's also less taxing on fluid separation processes. So here we're looking at a polymer flood test that we run in our laboratory. The first video you see, we have the red color is oil, and in the top video, we have a water injection happening. And you can see that it clearly fingers through the porous media. When we move on to the second video, we have the polymer flood coming into the system, and it's shown in green. And we can see that we see the polymer filling in a lot of the gaps where water bypassed the oil. Once we inject polymer, there's a much better sweeping of oil near the injector. And we also see it do an excellent job of reducing the viscous fingering and improving conformance control throughout the process. I'm also going to show you another video of a type of polymer flooding that we performed with a client. So in this first video, what we see here is a comparison of a high-loading polymer against a low-loading polymer. What's really interesting in this project is that we found that the ultimate recovery of both polymers was about the same. So at the end of a 12-hour or a few pore volumes of injection, we found that there wasn't a significant difference in recovery between the low and the high loading. But what we did see is that the high loading polymer clearly increases the rate of production and has significantly higher production in the first few pore volumes. So what this shows is there's a few options in the field. One option is to start with a high viscosity polymer and gradually decrease the viscosity because we see ultimately the same recovery. And this can improve the economics of a polymer flood. Another project we ran here was, comparing the high viscosity polymer that you saw in the previous test against a comparable viscosity fluid, but significantly cheaper than the high viscosity polymer. So what we see here is that both of these polymers achieve a very similar recovery factor. This meant that our client may be able to substantially cut polymer costs by over 50% without reducing oil production. So the application of microfluidics results produce a very high correlation as well against core flooding and field results, predicted field results. So why do our clients buy into our testing? So interface microfluidic testing for EOR, it only takes 1 day per measurement. And the fabrication of our devices very accurately mimics the pore throat size distribution of the reservoir, making it a really great analog, a really great tool to screen through multiple conditions very fast. Because of the speed, this technology can be used to really hone in on the formulation and the concentration to arrive at optimal chemistry for your reservoir. Another application of microfluidics is analyzing mitigation strategies for thief zones using techniques like polymer flooding. This is an example of conformance control with a very heterogeneous porous media. So in this study, we looked at a device that had 4 sections of different permeability and porosity, ranging from almost 1,000 Darcy down to 1 Darcy permeability. Before I touch on the results, though, just briefly explain thief zones. So thief zones are large areas of the reservoir that steal injected fluid because they offer a path of least resistance, which is a consequence of that zone's low permeability. Polymer flooding helps solve this problem by increasing the viscosity of the injected water, which improves mobility and results in better conformance and higher oil recovery. It's important to utilize microfluidics here because core and sandpack models cannot isolate the thief zone's impacts and look at specific permeability and porosity zones that impact the results. So in this microfluidics test, the chip we designed contained 4 connected but distinct zones with the permeability decreasing from the top zone to the bottom zone. This was achieved by varying each zone's pore depth and porosity. Results of the test showed rapid brine fingering into high permeability zones K1 and K2. Once breakthrough to the production side occurred, the first thief zone formed. The corresponding displacement efficiency was decent for the first zone at around 46%, but dipped as low as 3.6% for the lowest permeability zone, which suffered the most due to the formation of the thief zone in the highest permeability layer. Even as we continue to inject water in this example, very little additional oil recovery occurs in that zone. So after polymer injection, the recovery in the K4 zone increased noticeably to reach around 60%. So researchers recommend polymer flooding as a secondary method to prevent early breakthroughs and reduce water consumption. So this research here is actually published in the journal Fuel and goes into more detail on how we perform this analysis. So if you have interest in reading this paper, please feel free to reach out after the webinar, and we'd be happy to send that over to you. So now I'm going to go on to CO2 EOR. So an area that Interface works a lot on is enhancing oil recovery using miscible CO2 streams. This is a well-established method that has historically been viewed as fairly economical, but as climate change mitigation becomes a priority, CO2 EOR is favored for its sustainability. In CO2 flooding, injected pressurized carbon dioxide traps oil, allowing it to float more easily to the wellhead. It has been shown to increase oil recovery by 10 to 25%. So essentially what we're doing here at Interface in this example is we're looking at how CO2 streams and the oil interact underground. We conduct all of these measurements at reservoir conditions, and we're able to also go into more detail on quantifying the actual impurities in the gas stream, on how they impact MMP, and how they may impact the ultimate performance of a miscible CO2 flood. So when we talk about gas injection, we have to talk about minimum miscibility pressure because it's critical that we achieve MMP for a successful miscible gas injection project. So one thing about doing these miscible injections is that it's very operator dependent, it's very reservoir dependent, and it can be very pricey. It's also very challenging to obtain the right CO2 stream for the flood, and it's important to know how that CO2 may impact the actual performance. So what Interface has done is we've taken the traditional slim tube measurement, the traditional slim tube equipment, and we've shrunk it down onto our platform for ease of MMP measurement and analysis. So in this first video here, what I want to show you is a demonstration of an immiscible gas injection case. Here we can clearly see the gas, which is the dark color, is fingering through the oil, which appears white in this video. We see high residual oil left inside of the device after the injection. On the other hand, when we look at a miscible case, we see that as the gas is injected, initially there is some fingering, and then it starts to develop this transition zone, and it becomes completely miscible towards the end of the flood. We see very little residual oil left in the device upon completion of the testing. So why would we use microfluidics for MMP? Well, it's quite simple. It's a lot cheaper, it's faster, and we're able to produce high quality data. So we've actually increased the number of MMP measurements that we can deliver to our clients by over 20 times. So instead of the 4 to 5 measurements that you receive from a slim tube, and then you take those and interpolate them, we're actually able to deliver a high quantity of MMP results, which eliminates the need for interpolation and improves the results overall. We're also able to reduce the sample size required considerably, reduce the time, and reduce the cost. So a typical MMP measurement for Interface Fluidics takes about 3 to 4 days after we receive the oil sample in our laboratory. And just to compare to slim tube, that measurement typically takes a few months. So an exciting application of our technology comes through our work with an Alberta-based CCS operator. We're helping a client monitor and optimize the injection of industrially captured CO2 streams with varying impurities. The exciting part about this project is that we're actually conducting the test with our new compact deployable unit in an offsite lab. So in this project, the reservoir pressure is very low, and it's important to be deliberate with the composition of gas that is being injected and being aware of how impurities in the stream may impact operations in the field. So our goal is to understand the impact that different impurities can have on a CO2 stream, ultimately helping our client plan their field operations. The fact that we've created a portable deployable testing unit to an offsite lab also shows the future of how reservoir fluids and analysis are coming to a point of care model. So the increased convenience also means that continual monitoring of MMP is possible in order to stay ahead of changes in EOR conditions. So another application of CO2 that we look at is with CO2 foams. Foam flooding is often used as well in enhanced oil recovery. And what they do is they essentially help with the mobility ratio of the injected gas into the reservoir. So the foams increase the CO2 viscosity and they help increase production. As reservoir compositions vary, it's important to understand how foams propagate through porous media, as well as being able to screen through different chemistries for the right surfactant and the right additives to that gas stream to help with production. So the work that I'm showing here was conducted with Aramco Services. It's been published in Nature Scientific Reports. And essentially what we did in this work is we looked at high temperature, high pressure screening of supercritical CO2 foaming agents. So in this graph, what you're seeing is an analysis of the actual foam half-life over time. And we're able to look at different weight percent of the surfactant additives, as well as different additives, and observe which surfactant has the greatest viability for these extreme conditions that we were looking at. We're also able to look at the foam pressure drop, mobility reduction factor over time. And one of the great things about doing this in a microfluidics application is that we can actually observe what's happening in the confined porous media. So typically, foam screening is done in column testing to measure the stability of foam, but it lacks the porous media and it lacks the representative reservoir conditions. So another advantage of this is not only that it takes so much less time and less fluid, but we're also able to do all of this analysis at reservoir conditions. So there's a lot of different applications of EOR that we haven't touched on today in this webinar. One of those is ASP flooding or alkaline surfactant polymer flooding, as well as nanoparticle applications. So the beauty of Interface's microfluidics platform is that we have a device where it's essentially a safe space to try out many different applications without fear of ruining a core or wasting all of that time on a core flood. But we're able to take these specific chemistries and look at how they perform in your reservoir with your reservoir fluids, and determine any improvement or potential reservoir damage that they may cause in a representative space. So another EOR application that Interface works on is SAGD. Our company was actually spun out of the University of Toronto many years ago from a project that we were working on with SAGD. So in this space, we have a different analog where we're able to look at the unconsolidated sand reservoirs, where we can screen through many different additives to the steam stream and be able to identify how that changes, improves the performance of the flood. So all of this testing is performed under controlled conditions. The steam temperature and pressure is consistent, and we're able to have visual access to the porous media, which enables us to identify different things like asphaltene deposition, steam chamber growth, steam to oil ratio. And another interesting thing that we're able to do in this device is also identify residual solvent levels and analyze retention of solvents in the porous media. So it's important not only to identify optimal conditions, but look at where the economics in the project, where the economics and the environmental impact of the project may be improved. So I'll just quickly touch on our technology. So Interface does all of our design, fabrication, testing, and analysis in-house. We're able to offer many different products from enhanced soil recovery, minimum miscibility pressure, safety, PVT, flow assurance. We also work in the frac fluid optimization space, regain conductivity testing, and more. All of our tests are conducted at reservoir temperatures and pressures. We're able to go up to 1,000 bar and 200 degrees Celsius. So the advantage of microfluidics overall is that we can do a lot of really interesting screening really fast, and it's a fraction of the time and cost of traditional laboratories. Interface's contribution to EOR ranges from analysis of polymer, surfactants, nanoparticles, CO2 foams, safety additives, and more. We can also look at the pore scale behavior and understand what is happening at that pore scale. So with our technology that we've developed, we are able to help the industry screen through multiple different cases really quickly to get you better data faster and help you lower your emissions. So with that, I'll turn it back over to Lee and open up the floor for questions.
All right. Thank you, Jelayne. We do have a couple of questions, and I believe one of them may already have been answered. So that was, have you tested using CO2 foam? So if we didn't answer that question well enough, feel free to send us an email to that webinar at interfacefluidics.com. But we've got a couple others here. Do you also work with unconventional reservoirs?
Yeah, so a couple of great questions. I'll just go back to the CO2 foam one really quickly. I did screen through those slides really quickly, but we do have actually a webinar that goes through CCS. It touches on our foam, MMP, and everything we're doing in that space. So I'd be happy to connect with you, James, after the webinar and link you up to some more of our resources, as well as send you that paper that we wrote with Aramco. In terms of the second question with unconventional reservoirs, yes. So I briefly touched on the end there that we do fracturing fluid optimization. So Interface has a whole suite of testing dedicated to unconventionals, where we're able to replicate the unconventional reservoir to very extremely low confinement. So we're looking down to sub 80 nanometer levels for pore throat size. Which enables us to screen through a lot of different chemistries for frac fluid, for frac applications.